Hello, me and Arthur are welcoming you to my home, and today um, we're going to go over the last two derivative rules. Um, we've put them off for a while. Um, these are the last two major rules. There's a couple minor variations on these, and now is the time to introduce them after you have a little bit of a knowledge of integrals. All right, so a reminder, we have the power rule, right? So the idea of the power rule is if you have some power, like x to the first, and you take the derivative of it, the power comes down, and then you subtract 1 from the power. So you kind of get this idea, if you go one level higher, dx of x squared gives you 2x. It actually gives you, you get this constant, but if you take the derivative of something with squared, you get a linear term. If you take the derivative of something linear, you get constant term, so it's 0 power. And it's the same if you have negative. So if you have x to the negative 1, you take the derivative, same thing happens. You get negative x to the negative second. So you have this kind of tower of powers. So if you want to go down in power, if you want the power to go down, you take the derivative. Likewise, if you want to go up, you take the integral. So the integral of any constant, dx, gives you that constant times x plus some other constant. We'll talk about indefinite integrals at some other time and make sure that you get that in another rule. But basically, if you take the integral here, you go up to linear. If you take the integral of a linear term, you go up to x squared. Same thing if you're down here. If you take an integral of x to the negative second, you end up with some term times x to the negative first, right? So you have this kind of order where it's like x to the third, x squared, x to the first, x to 0, and then x to the negative, x to the negative 1, x to the negative second. You go down the tower with derivatives. You go up the tower with integrals. But there's a problem. We know it doesn't work for x to the negative 1, which is also written as 1 over x. It's obvious that the power rule can't help us with the antiderivative. I say obvious, I probably shouldn't say obvious. Let's try it. If we want to take the integral of 1 over x dx, and we want to use the power rule, well, this is x to the negative 1 dx. So by the power rule, we'd get an antiderivative of x to the 0 divided by negative 1, which doesn't seem right, because it's just a constant, so any definite integral would just always be 0. It just doesn't quite seem right. Okay? So we're going to do a thing where we're going to do an exploration where we imagine some antiderivative exists, and we see what its properties are. And just for shortness, it needs a name, so we're going to use capital L. So basically, capital L is the antiderivative of 1 over x, so that means if we take the derivative of L of x, we should get 1 over x. Okay, so this is the setup. Like, we don't know what it is, but we know when we take its derivative, we get 1 over x. Okay, we actually want to kind of make that more precise. So let's think about, what does 1 over x look like? Well, if we graph it, it looks like that. So certainly, you can, like, it makes sense. So we should make sure that, like, it makes sense to talk about an antiderivative existing. And if you look at here, well, certainly this area is pretty well defined. As long as we stay away from 0, 0 seems to be a danger zone. We can get a well-defined area that should be some function that changes. So we're going to be a little bit more precise with our L. Our L of x we're going to define as the integral from, again, staying away from 0, from 1 to x of, and just, this is a bookkeeping thing. You need a dummy variable. It's called dummy variable. So when you do this integral, the t's go away. And that'll all work. So we're just going to set this as our basis at 1, and then just move x wherever we are. And this area is going to be our L of x. So from the start, by this definition, L of 1 has to be 0 because you're going from integral of 1 to 1. So that's always equal to 0 no matter what. And we know the domain of L. Well, if we let x go to 0 or negative, we'd have to somehow get an area from infinite, like we'd have this infinite spot. And that seems like a problem. So let's just exclude that, right? So we're going to say that our domain of L of x is from 0, not including 0. But if we look over here, we can probably put x as far over here as we want. So let's say it's from 0 to infinity. And that seems reasonable just based on the definition in the picture. Right? And then, let me just look ahead. This was the last thing I wanted to do. Okay, yeah, that's the one. Those are the things I wanted to do from the picture. So we have this idea where, again, L of x is the integral from 1x of 1 over t dt. Let's just start playing around, right? What would happen if we took, like, what do we know if we slipped in a constant? So instead of x, we had some constant times x. Like, what can we say about that? Well, just by itself, we can't really say much. But we could take the derivative, right? And see what happens. So if you take the derivative of L of c of x, you get, of course, the derivative of capital L is 1 over, and then by the chain rule, you have to multiply by the derivative of c of x, so times c, which cancel out, and you get x, which is just the same as the derivative of L of x. So that's weird. We put in a constant multiplier and it didn't change the derivative at all. Well, the only way that could happen is if putting in a constant multiplier here has to equal that plus some other constant, right? Because the derivative constant is 0. So just from exploring our possibilities, we know this has to be true. So that's the only way you can get the derivative of this equal to the derivative of this. So, all right, well, that seems weird. It seems like something's weird going on with multiplication. So let's try repeated multiplication. Let's try raising, one of the simplest derivative things, raising x to the power of n, and then taking the derivative of that. What do we get? Well, we get 1 over x to the n times, we have to use the power rule and the chain rule, so that would be times n x to the n minus 1. Now, wait a minute. You have x to the n minus 1 on top, x to the n on bottom. Those cancel each other out, except for a factor of x to the negative 1. So that's just equal to n times 1 over x, which is exactly the same as n times the derivative of L of x. So from this, we know that L of x to the n has to have some relationship where it's n times L of x. That's a heck of a property right there. And all we did to prove it was just use derivative rules. So to recap, we have these 4 properties where you put in 1, you get 0. We have its domain, it's defined from 0 to infinity. You can multiply inside by a constant, and that seems to not change much. There might be an addition of a constant, you don't know. And then you can even raise what's inside to a power, a constant power, and that just spits out as a multiplier. So it seems like something very strange here is going on with multiplication, right? So let's try some other stuff. What about addition? What happens if we add two L's, right? L of x plus L of y. What would that equal? And just for generality and for the fact that all we have here is taking the derivative, let's, instead of doing just this, we'll do what is the L of f of x plus the L of g of x, right? And again, all we have is taking the derivative, so let's see what happens when we take the derivative here. The derivative of this is going to be 1 over f of x times prime of x. And then we have plus 1 over g of x times g prime of x. Okay, well, that's pretty simple and not very illuminating. So one of the things we can do when we're like, this doesn't tell us much, we're adding fractions. So let's add fractions. What do you do when you add fractions? Well, you need a common denominator. So to get a common denominator here, we're going to start with our slightly simplified fraction, and we multiply by the factor that's missing. And then on this other side, you have the slightly simplified fraction here, and you multiply by the factor that's missing. So this becomes g of x f prime of x plus f of x g prime of x over f of x times g of x. Now at this point, if you've been following along and like being on your derivative rules, this should be screaming out at you, because this numerator, that's the result of the product rule. And down here, well, that's the product of f and g. So you should get this exact form if you took the derivative of L of f of x times g of x. Let's review. So derivative of L, you put that in the bottom, so you get f of x times g of x. But then, by the chain rule, you have to multiply by the derivative of f of x times g of x, which is just this expression here. Wow. So that's really kind of an interesting feature. You have multiplication on the inside. You can turn that into addition on the outside, or vice versa. If you have addition on the outside, you can turn that to multiplication on the inside. Well, that's the case, what about division? Let's try it the other way. Just so we had the idea of like starting with addition got us to multiplication. So let's try it with division. So we'll start with L of f of x divided by g of x. And see where that gets us, right? So taking the derivative, that gets us to 1 over that, or 1 over this fraction, which just for our concerns, we're just going to flip the fraction. So that's going to be g of x over f of x. Now we're going to multiply that times the derivative of this, right? Well, we're going to have to use the quotient rule for that. So that's going to be g of x f prime of x minus f of x g prime of x over g of x squared. All right, so we have all of this multiplied out. Let's start simplifying. This g of x cancels out this g of x. You can split the fractions across the subtraction. So you get g of x f prime of x over f of x g of x minus f of x g prime of x over f of x g of x. And again, like this f of x and this g of x are what give our two denominators. And then on this one, these cancel. On this one, these cancel. So we get f prime of x over f of x minus g prime of x over g of x. Well, that's exactly what we wanted. This is the derivative of L of f of x. This is the derivative of L of g of x. So the derivative of f of x divided by g of x is equal to the derivative of L of f minus L of g. So let's summarize again. So we have all these from earlier. We know if we have L of f times g, that has to be kind of equal to L of f plus L of g. If we have L of f divided by g, that equals L of f minus L of g. What function has these properties? I'm just going to remember from pre-calc, something has this collection of properties. And we call those logarithms. Logarithms have that set of properties. All logarithms have this set of properties. More specifically, we are here going to define the natural logarithm function. So we're going to say the natural logarithm function, which we write as ln of x, is defined to be the integral from 1 to x, 1 over t dt. So that the derivative of ln of x is 1 over x, and the integral of the indefinite integral of 1 over x dx equals ln of x plus some constant. This is why this was always called the natural logarithm, right? Because it is the simplest logarithm that comes from calculus. Right? There are other logarithms, but this is the one that comes from the simplest integral in calculus, and that's why we call it the natural logarithm. Well, that was logarithms, and it's nice that we were able to like figure out where logarithms fit in, but you may remember there's another class of functions from pre-calculus. It's the exponential functions. Usually we get to those first. So what can we say about exponentials? And since we're talking about natural logs, why don't we worry about y equals e to the x and just try to figure out what is the derivative of e to the x. from e to the x, maybe we can worry about some of the other things, right? And so we could just write the derivative signs, but we wouldn't necessarily get anywhere, because again, we don't really have any knowledge here. But we do have knowledge of natural log, right? So what happens if we take the natural log of both sides? From our natural log properties, we know that this is equal to x natural log e. Right? So when we take the derivative of both sides, we get on this side 1 over y times dy dx. And on this side, we just get the natural log of e. Right? And so we can we haven't talked about e. You may not necessarily remember that this is the case from pre-calc, but the natural log of e, well, that's just equal to 1. So we get 1 over y times dy dx equals 1. You can multiply both sides by y. We get dy dx is just exactly equal to y. Well, but y is equal to e to the x. So the derivative of y is also e to the x. So e to the x is one of these special cases. It's the only special case like this, where the derivative of the function is just the same function back at you. So the derivative of e to the x is just e to the x. And we get that using our log properties. So in conclusion, these are the two major properties. And in another video, when this guy's a little bit settled down, we'll talk about doing this for other bases, right? We just have natural log, we have e to the x. We can get into when the base isn't e, who knows, but the derivative of e to the x is e to the x. The derivative of natural log is 1 over x. So when you're thinking about going backwards, if you need to integrate e to the x, well, again, it's just e to the x. If you need to integrate 1 over x, that gets into natural log. So thank you for stopping by.